Esteemed colleagues, today we shall examine a series of persistent anomalies in particle physics. These are not minor discrepancies, but rather profound challenges to the Standard Model, our most successful theory of matter. We will explore a rather provocative theoretical framework proposed to resolve them. A framework that suggests our known universe of particles may be just one layer in a much deeper, scaled hierarchy of physical law.
We will proceed methodically through our investigation today. First, we will establish the foundational problems, these cracks in the edifice of the Standard Model. Then, we will introduce the central hypothesis of a scaled physics. And finally, we will scrutinize the purported evidence and consider the truly profound implications.
So, let us begin by delineating the boundaries where the Standard Model's otherwise formidable explanatory power begins to falter. These are the experimental results and observations that, for years, have resisted any and all attempts at a conventional explanation. As this compendium illustrates, the list is long and varied. It includes deviations in the masses of fundamental bosons, the magnetic moment of the muon, and the unexpected complexity of hadronic states. You see, from the largest colliders to the most sensitive dark matter detectors, a consistent picture is emerging. One of a universe more complex than our current theories can accommodate. Now, let us focus our inquiry on one of the most recent and perhaps the most perplexing of these anomalies, the observation of a hadronic state known as toponium. The problem is quite simple yet profound. According to our understanding of particle physics, this state should not exist. Conceptually, toponium is straightforward. It's a quarkonium state, analogous to charmonium or bottomonium, formed from the heaviest known elementary particle, the top quark, and its antiparticle. However, its very existence presents a fundamental temporal paradox, a direct conflict with the known laws of quantum chromodynamics. And here is the heart of the issue. The top quark is an incredibly ephemeral particle. Its lifetime is on the order of 5 × 10⁻25 seconds. The process of hadronization, however, the process by which quarks bind together via the strong force, requires a significantly longer duration, about 10 to the minus 23 seconds. The constituent particle decays at least an order of magnitude faster, and in some estimates nearly 2 orders of magnitude faster, than the time required for it to form the bound state. So this question really encapsulates the central conflict. How can this particle be observed? Our standard intuition from quantum chromodynamics is unambiguous. It's impossible. And yet, major experimental collaborations like ATLAS and CMS have reported its existence. We are faced with an irreconcilable conflict between our theoretical framework and empirical fact. In the face of such a paradox, we must be open to novel theoretical frameworks. The source material for today's discussion posits a radical solution, one derived from a theory called Topological Geometrodynamics, or TGD. It asks a profound question. What if the toponium we observe is not a particle of our physics at all, but a visitor from a much heavier, scaled-up copy? The core of this hypothesis is the idea of a fractal hierarchy of physics. Imagine our Standard Model is just one layer. TGD proposes the existence of other, parallel layers. The specific one of interest here is called M89 hadron physics, a nearly identical copy of our own particle physics, but operating on a mass scale that is vastly greater. And central to this hypothesis is a very precise scaling factor, 512. This is not an arbitrary number, not a parameter tuned to fit the data. Rather, it is derived directly from the mathematical formalism of the theory, specifically from the ratio of p-adic length scales associated with 2 Mersenne primes, M107, which corresponds to our hadron physics, and M89. So how might we access such a physics? The theory suggests that in the extreme conditions of a particle collider, a state of so-called quantum criticality that might be what we misidentify as quark-gluon plasma, a phase transition can occur. This transition could alter fundamental parameters, like the effective Planck constant, which would in turn slow the decay of M89 particles, giving them sufficient time to form. The paradox would be resolved. Now, this is a fascinating and elegant theoretical proposal. But a theory is only as good as its ability to match observation. So let us now move to the evidence, where this M89 hypothesis is applied to reinterpret existing particle data. If correct, it should shed new light on particles we thought we already understood. And here we encounter the first central and quite startling claim.
The theory posits that the particle we have long identified as the top quark is, in fact, the strange quark of this heavier M89 family. And observe the numbers. When one takes the mass of an ordinary strange quark and applies that scaling factor of 512, the predicted mass is approximately 176 GeV, which is remarkably close to the measured mass of the top quark.
The corroboration does not end there. Very recently, the LUX-ZEPLIN dark matter experiment reported a potential signal, a candidate particle with a mass of about 67 GeV. Now, what does the M89 theory predict? If you take the mass of an ordinary pion, a very common hadron, and scale it up by that same factor of 512, the predicted mass of the M89 pion is, precisely, 67 GeV. The alignment with the data is frankly stunning.
Furthermore, the hypothesis is not limited to reinterpreting just two data points. It generates a series of concrete, falsifiable predictions. As you can see, it provides mass predictions for a whole host of M89 counterparts, from the charm and bottom quarks all the way to a heavy electron and nucleon. This provides a broad set of claims that can be tested at the LHC and future colliders.
Should this theoretical framework prove to be valid, the consequences for particle physics would be, without exaggeration, profound. This would not be an incremental advance, but a genuine paradigm shift in our understanding of the subatomic world.
We are not merely discussing a few anomalous particles here. We are contemplating the existence of an entire, undiscovered, parallel spectroscopy of hadrons. Everything we know, all the mesons and baryons, may just be the tip of a much larger iceberg. Beneath the surface could lie a complete, scaled-up version of hadron physics, awaiting discovery at higher energy scales.
And the discovery of such a shadow physics could resolve other deep mysteries. It offers a potential explanation for apparent violations in the CKM matrix, which governs quark mixing. It could provide a topological, rather than mechanistic, reason for why fundamental particles appear in three distinct generations or families. It opens up an entirely new realm of phenomenology to explore. Ultimately, this leaves us at the frontier of theoretical physics. Do these persistent anomalies, the Toponium paradox, the W-mass, the muon G2, signal a new, deeper layer of physical reality, or are they merely intricate puzzles that will eventually be resolved within our existing framework? The answer, one hopes, lies in the next generation of experiments, and with it, perhaps, a new understanding of the universe itself.